Picture a planet so massive, it makes Jupiter look small. A world so puffy that its density is lower than a marshmallow. A giant that's literally evaporating into space at millions of tons per second, leaving behind a tail of helium gas stretching hundreds of thousands of miles through the cosmos. This isn't science fiction. This is HATP 67b, and it's one of the most extreme worlds scientists have ever discovered. Before we dive into this cosmic mystery, if you're fascinated by the weird and wonderful planets beyond our solar system, make sure to hit that subscribe button and turn on notifications so you don't miss any of our space exploration content. Today, we're going to explore a planet that's rewriting what we thought we knew about planetary physics. We'll talk about how it got so absurdly large, why it's disappearing before our eyes, and what its doomed fate tells us about the evolution of worlds across the universe. The story of HATP 67b begins with the Hungarian Automated Telescope Network, or HATNET for short. This network uses small, wide-field telescopes positioned at two observatories, the Fred Lawrence Whipple Observatory in Arizona and the Mauna Kea Observatory in Hawaii. Their mission? To scan the night sky looking for tiny dips in starlight that might indicate a planet passing in front of its star. Between 2005 and 2008, HATNET captured observations of a star designated H8P67. When astronomers analyzed the data, they noticed something interesting: periodic dips in the star's brightness that repeated every 4.8 days. This pattern is the telltale signature of a transiting planet. But detecting the transit was just the beginning. Confirming that this was actually a planet required years of follow-up observations. The problem was that H8P67, the host star, rotates very quickly, which made it difficult to measure the tiny wobbles caused by the planet's gravitational pull. These wobble measurements, obtained through what's called the radial velocity method, are crucial for determining a planet's mass. So what exactly is HATP 67b? Let me paint you a picture with some mind-blowing statistics. First, the location HATP 67b orbits a star that's about 1/200 light-years away from Earth in the constellation Hercules. To put that distance in perspective, if you could travel at the speed of light, it would take 1/200 years to reach this system. With our current spacecraft technology, the journey would take tens of millions of years. The host star, also called HATP 67, is what astronomers classify as an F-type subgiant star. It's significantly larger and more massive than our Sun, about 1.7 times the Sun's mass and 2.6 times its size. The star is also much hotter, with a surface temperature of around 640 Kelvin compared to the Sun's 778 Kelvin. But here's the kicker. This star is evolving. It's on its way to becoming a red giant, which, as we'll discuss later, spells doom for HATP 67b. Now let's talk about the planet itself. HATP 67b has a radius that's approximately 2.14 times larger than Jupiter. To give you a sense of scale, Jupiter has a diameter of about 850 miles, or 143,000 kilometers. That means HAT 67b is roughly 190,000 miles, or 306,000 kilometers across. That's huge, but here's where things get really weird. Despite being more than twice Jupiter's width, HAT 67b has only about 45% of Jupiter's mass, according to the most recent measurements. This creates an absolutely bizarre situation. The planet has a density of approximately 0.06 grams per cc. That's right, 0.06. For comparison, Jupiter has a density of about 1.3 grams per cc, while Earth clocks in at 5.5. A marshmallow has a density of around 0.2 to 0.3 grams per cc, making HATP 67b less dense than the treats you roast over a campfire. In fact, HT67b is currently recognized as the second lowest density hot giant known to science. Only one planet is puffier, and that makes HT67b an extraordinary laboratory for understanding extreme planetary physics. HT67b is what astronomers call a hot Saturn, or sometimes a hot Jupiter, depending on who you ask. These terms refer to gas giant planets that orbit extremely close to their host stars. How close? HT67b orbits at a distance of just 0.065 astronomical units from its star. An astronomical unit, or AU, is the average distance between Earth and the Sun, about 93 million miles. At 0.065 astronomical units, HT67b is orbiting at about 6 million miles, or 9.7 million kilometers from its star. That's closer than Mercury is to our Sun. At this distance, the planet completes a full orbit in just 4.81 days. Think about that. This world's entire year is shorter than a single week on Earth. The planet's orbit is nearly circular, with an eccentricity close to zero, and it's very well aligned with the star's rotation. The projected spin-orbit angle is just 2.2 degrees, which tells us something important about how this planet got to where it is today. We'll explore that more when we discuss formation theories. One of the biggest mysteries in exoplanet science is why some hot Jupiters and hot Saturns are so inflated. Based on standard models of planetary physics, these planets shouldn't be as large as they are. Jupiter-sized planets should have relatively similar radii, regardless of their mass, within a certain range. But observations keep finding planets that are significantly larger than expected, and HT67b is one of the most extreme examples. So what's causing this inflation? Scientists have proposed several mechanisms, and it's likely that multiple factors are at work. The first and most obvious factor is the intense radiation that HT67b receives from its host star. Being so close to a star that's hotter and more luminous than the Sun means this planet is getting absolutely bombarded with energy. The equilibrium temperature of HT67b is estimated to be around 1,900 to 2,000 Kelvin, which is roughly 3,000 to 140 degrees Fahrenheit, or 1,600 to 850 degrees Celsius. This intense heating doesn't just warm the outer atmosphere, it penetrates deep into the planet's interior. The energy gets deposited in the planet's upper and middle atmosphere, where it slows the normal cooling and contraction that a gas giant would otherwise undergo. In simple terms, the planet is being heated from the outside, which prevents it from shrinking to its natural size. But radiation alone doesn't explain planets as inflated as HT67b. Recent research suggests another mechanism might be at work: ohmic dissipation, also called ohmic heating. Here's how it works. When intense stellar radiation heats a planet's atmosphere, it can ionize atoms, stripping away their electrons. This creates a layer of ionized gas, or plasma, in the atmosphere. Now, if the planet has a magnetic field and is rotating, this ionized gas can interact with the magnetic field in complex ways. The planet's rotation drags the ionized gas through the magnetic field, which creates electrical currents. These currents generate heat through a process similar to electrical resistance heating, like the heating element in a toaster. This ohmic heating can deposit enormous amounts of energy deep in the planet's atmosphere and interior, causing further inflation. The fascinating thing about ohmic dissipation is that it works most effectively in a specific temperature range, roughly between 1,500 and 2,000 Kelvin. Below this range, there isn't enough ionization. Above it, the conductivity becomes so high that magnetic braking slows down the atmospheric winds that drive the effect. HT67b, with its equilibrium temperature around 2000 Kelvin, sits right at the edge of this sweet spot for ohmic heating. There's also the possibility of tidal heating, though this is likely less significant for HT67b given its nearly circular orbit. Tidal heating occurs when gravitational forces from the star squeeze and stretch the planet as it orbits. If the orbit is elliptical, the intensity of these forces varies, causing the planet to flex. This flexing generates heat through friction in the planet's interior. However, since P67b's orbit is nearly circular, tidal heating is probably not the main driver of its inflation. Here's where the story gets really interesting. Recent studies have shown that P67b's extreme inflation is likely related to the recent evolution of its host star. Remember how I mentioned that P67 is becoming a red giant? As stars evolve off the main sequence and begin this transformation, they become more luminous, meaning they output more energy. For most of P67b's existence, the star was less luminous, and the planet was probably more normal-sized. But as the star has brightened over the past few 100 million years or so, the increased radiation has caused the planet to heat up and expand dramatically. In other words, we're catching this planet at a very specific moment in its evolution, when it's transitioning from a relatively normal hot Saturn to an extremely inflated, rapidly evaporating world. This timing also explains why ultra-low-density hot Saturns like P67b are so rare. Most planets in this configuration would have already evaporated away. P67b exists because its star only recently became luminous enough to trigger this runaway inflation and evaporation process. P67b is a planet of extremes, the largest in terms of size, one of the least dense, and one of the most rapidly evaporating. It's a world that shouldn't exist for long, and yet we're here to witness it. This puffed-up giant, with its massive helium tail and doomed orbit, is teaching us about the limits of planetary physics, the violence of atmospheric escape, and the ultimate fate of worlds caught too close to their dying stars. As we continue to discover and study exoplanets, we'll undoubtedly find more bizarre worlds that challenge our understanding. But P67b will remain special. A cautionary tale of what happens when a planet is in the wrong place at the wrong time in its star's evolution.